Hey kiddos, how we doing tonight? Everything good? Hope you had a great weekend. Um, had great weather on Saturday, not so great on Sunday, and then today wasn't so great either. Kind of off and on, I guess. I guess it wasn't bad. Anyway, I hope you had a great one. Excuse me. Um, excuse me. Today I want to go over a couple questions off of your homework, and then we'll teach the next lesson. I need to shave. Um, and we'll go over we'll do that. So y'all guys asked for number 60. That's a tough question. I actually started the lesson over that and got messed up, so I had to start this whole thing over again. And then I had another student ask for number 50, so I want to go over that one just a little bit. I'm going to guess that most of you guys figured that out, but I do want to cover something that's on that. And so let me go to the homework. There's number 60. Here's number 50. Let me close myself up a little bit. Put me over here. Number 50. Hopefully, we figured out R was this negative 1/2. So that wasn't that big of an issue. You plug in 0 to get the first term. So hopefully, that wasn't a big deal. Plug in 7 to get the last term. Now, the deal is, oh, guys, you got to see that your N is actually 8, because you got to start off with 0, which counts as 1, and then you got to go 1, 2, 3, 4, 5, 6, 7, and that's why you get N to be 8. And so that's a little bit different. You don't always have to start off with 1 right here. You don't always have to start off with 0 like in these. You could start off with 3 or 4 or 5. Who knows what this value down here in the bottom could be. That could be anything. So just kind of want to cover that on that particular question. It's something that I did not do a big job on in explaining these things. So just recognize that. Number 60, I had several of you guys ask about this one. And we'll kind of walk through it here. It's the Sierpinski carpet. It's a fractal created using squares. The process involves removing smaller squares from larger squares. First, divide the large square into 9 congruent squares. Remove the center square, and then repeat that process for each smaller square. And so you can see we initially, or stage 0 if you want to, is one big square. And so you have one big square over here for stage 0. Here's stage 9. We broke it up into stage 1. We broke it up into 9 parts, removed the center square. And then we broke each one of these squares up into 9 parts and removed the center square. And then we broke each one of these up into 9 parts and removed the center square. And we will continue on throughout so many stages. Okay? Remove the center square. Repeat these steps for each smaller square as each so on. Okay? Let A sub n be the number of squares removed at the nth stage. Find a rule for A sub n. I hope this wasn't too bad for you. This is very similar to the honeycomb problem. In stage 1, hopefully this was not too bad. You removed 1 square. In stage 2, we removed 1, 2, 3, 4, 5, 6, 7, 8 squares. We don't have to count this one. We already removed that one in stage 1. In stage 3, we removed 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 there. 1, 2, 3, 4, 5, 6. There's 6 there. This is 9. This is 6. This is 1, 2, 3, 4. Here's another 6. Here's another 9. Here's another 6. And here's another 9. 9 and 6 is 15. 9 and 6 is 15. We're at 30. 6 and 9 is 15. 6 and 9 is 15. That's 60. And here's 4 more. So we removed 64 out of stage 3. So out of stage 1, we removed 1 square. Out of stage 2, we removed 8 squares. And out of stage 3, we removed 64 squares. Let me pull up my paper right here. Let's turn the light on. That's better. Okay. So we can see from here, guys, that I multiplied 1 times 8 and 8 times 8. So my D value, and it's not D, I'm sorry, well, R value, ratio, R is 8. Sorry, guys, I swallowed wrong. A sub 1 times R to the n minus 1. And a sub 1 is simply 1, so I don't even really need to put that if I don't want to. R is 8, and it's to the n minus 1. And so that's the formula for that the number of squares removed at any level. Okay. Now let A be the number of so B part. I think that's A part. We're good. Oh, find the total number of squares removed through stage 8. So I'm just going to go A sub n is equal to A to the 7th power, and I have to go with the old calculator here for that because I'm not doing that. 8 to the 7th is 2097152. 2097152. Boom, boom. And y'all can't see any of that because I didn't there. Okay. All right, B part, and this was the tough part. B part was tough. Let B be the remaining area of the original squares after the nth stage. Find a rule for B sub n. So I got this. I think B sub n, the summation of this is, what is it? It's 1 minus r to the n over 1 minus r. And I'm supposed to multiply that times n. Is that right? That's the summation. Where's my sum? I'm going to make sure. We got too many formulas too. You guys are lucky because you're going to. I would give you these formulas anyway. Oh, it's a sub 1. It's not n. Okay. All right. So we'll go back down here. I'm gonna go to my paper, I guess. We know what a sub 1 is. A sub 1 is 1. And so B sub n is 1. 1 minus r, and r is 8. And 1 minus r, which is 8. I think that's all we need for that. I think that's what it does. The amount of area left. Let's plug in 1. That would be 0. 1 minus 8. That can't be right. Is it n or n minus 1? Oops, I gotta go back here. Damn it. Yeah, it's n. Okay. So if I was doing the first stage, oh yeah, if I was doing the first stage, this would be 8 to the 1. 1 minus 8. 1 minus 8, that gives me 1. 1 times 1 is 1, and the area would be 1. Well, that wouldn't be right, because the area wouldn't be 1 after that. The area would be 8/9. I don't think that's right. Let me go back and do it. I'm gonna pause here. I got it now, guys. I even looked at the answer, and the answer, I don't think it's right. I don't know what they are doing. Um, So how much area is left? Let's look at the big square here. It's broken up into 9 sections. 1, 2, 3, 4, 5, 6, 7, 8, 9. How much is left? 8/9. And so let me change my paper over. So out of stage 1, 8/9 is left. And I'll bring it over to my paper in just a second. Stage 2, how much is left? Well, there's 1, 2, 3, 4, 5, 6. There's 8 here. So 8 times 1, 2, 3, 4, 5, 6, 7, 8. There's 64 left because there's 8 in each square. So on stage 2, there is 64 left, and this is out of 9 squares here, but you got to still include this because it's out of the entire thing. So 9, and there's 3 nines, or there's 3, 6, there's 9 nines, so it's out of 81. Are y'all kind of with me? Let's go over that again. There is 8/9 left. In this stage, there are 64 out of 81 left. That's what we're supposed to be doing. How much? Find the remaining area after find the remaining area. And so out of this one, remember how many I removed now? This is 1/9. And so I removed, if y'all remember, right? I removed how much is left. So there's 8 here. Yeah, I wish I could point better and I can't. I'm trying to use my finger. 8 here, 8 here. 1, 2, 3, 4, 5, 6, 7, 8. There's 9/8. 1, 2, 3, 4, 5, 6. And so we remember we counted that earlier. So this is 9. Here's 6. Here's 9. Here's 6. Here's 9. Here's 6. So um, what did we say? 8. I'm sorry, 8 left. 8. So 72 are left here because there's 8 each one, and it's 9 across. 1, 2, 3, 4, 48 here. So 72, 48. There's another 72. There's another 48. And then the next one, there's actually 1, 2, 3, 4. So that's a 32. And then there's another 48. There's another 72. There's another 48. And there's another 72. So is it 1, 2, 3, 4 72s? 4 72s. Here we go, calculator time. Why do you keep down on me? 72 times 4 plus 48 times 4 plus the 32 is 512. Out of 9, 1, 81, 2, 3, 4, 5, 6, 7, 8, 9. So there's 81 times 1, 2, 3, 4, 5, 6, 7, 8, 9. 81 times 9. 729. That's what's left. Let me go to my paper. Where's my thing? Down here, I think. There we go. So in stage 1, there was 8/9 left. In stage 2, there's 6481 left. Stage 3, there's 512 of a 729. So can we start to see a pattern? 8, 8 times 8, 64 times 8, 9 times 9, 81 times 9. So what's left is 8 to the n over 9 to the n. That's what's left. I don't know what that answer was, but there's no way that was right. That's what's left. And I think they wanted me to find it, how much was left after 12, after stage 12. And so I'm going to go stage 12. Oh, sorry, I'm going to go back to my paper. So stage 12, I'm just going to plug in 12. So 8 to the 12th over 9 to the 12th is what's left. 8 to the 12th divided by, my calculator messed up. Divided by 9 to the 12th. It'd be a really 0.24. 33. Oh, you can't read that. There, over there. I think that's what's left. I can see why y'all had a tough time with that. But the first stage, 8/9 is left. The second stage, so I broke each one of those 9 up into another 1/9, and I was removing 1/9 of it. And if I was removing 1/9 of it, that means 8/9 is left. And so how many 8/9 did I have? Well, I had however many I had. That's what's left. Okay, that's what's left. All right, I'm done with it. Let's go on. Put you over here. Let's go here. Let's go here. Let's go here. That's a neat thing that they have a triangle too that you can break it up into triangles and remove one each time. I think I'm supposed to do 7.4. Is that recursive? No, infinite. Okay. Let me make sure I'm supposed to do this one. Let me hit pause. Y'all don't need to see all this. Aha, good thing I looked because we're not supposed to do 7.4. We skipped that last year. I'll talk a little bit about it, but let's look at 7.5, recursive. So here we go, recursive. Infinite series and finite series, when you add those up, it's kind of interesting. So it's kind of like, it's not kind of like, but that square, whatever the name of that thing was, if you keep adding up or keep subtracting squares, eventually that sum is going to be nothing. That's what the total area is going to be, because you're just going to keep removing a bunch of squares and a bunch of squares. That ends up being kind of calculus. 7.5. Recursive. Okay, y'all will like this, I think. Focus. There you go. So far in this chapter, we've worked with explicit rules. I like explicit rules better than I like recursive rules. But the explicit rule gives a rule for that term. So if I want the 9th term, I plug in 9. If I want the 20th term, I plug in 20. That's an explicit rule. That's the one that we use a lot of. It's a lot easier to do. In this lesson, we're going to learn another way to find a sequence by using a recursive rule. And the opposite of an explicit rule, a recursive rule basically takes the previous term. And so you're doing something to the previous term. This is what a recursive rule looks like. So the big deal with a recursive rule is a lot of times what they're going to have to do is give you the first term. Or they have to give you a term. It doesn't necessarily have to be the first term. For instance, this one here, they didn't give us the first term. They gave us the 0 term, which is a little crazy because there's no such thing as a 0 term. But that's what they gave us, a 1. And so you can see this if I want a sub 1, I got to plug in a 1 right here. And then I got to plug in a 1 right here, which is 1 minus 1, which is 0. That means I'm going to use a sub 0, which is 1. And so 1 plus 4 gives me 5. And then when I want to plug in a 2, when I want the second term, then I need a 2 minus 1 here, which is a sub 1, which means I got to plug in the previous term, which was a 5. 5 plus 4 is 9. Then I got to do 9 plus 4, which is 13. So I just got to add 4 to each one of these. And so this is the recursive rule. Again, I don't like them as much, but that's what that is. Some of these are easier to figure out by using recursive rules as opposed to explicit rules. And this particular one, sorry, I'm bouncing me all over the place. Y'all don't watch me anyway. It's weird when I go over and look at myself, though, because now it's weird. A sub 1, the first term is 1. So here's the first term. Plug in 1 times 3 is 3. Plug in 3 to get 3, get 9. Plug in 9 to get 3 to 27. So you're just taking the previous term and multiplying it by 3. Arithmetic and geometric series in part 1, observe the differences of consecutive terms is a sequence that are constant. So the sequence is arithmetic, In part B, the ratios of consecutive terms are constant, so the sequence is geometric. So this is a arithmetic sequence, and this is a geometric sequence. So we could write those explicitly, or we can write them recursively. Okay? A sub n minus 1 plus d, where the d is the common difference. R times a sub minus 1, where r is the common ratio. All right. Here we go. Let's go to this example right here. Let me write these numbers down. We got 3, 13, 23, 33, and 43. And we got 16, 40, 100, 250, 625. Okay. I'll go here. Move me way back over here again. Now I'm not in the way. We can see that there's a 10 here, a 10 here, 10 here, 10 here. So the common difference. So the first thing you got to do is establish what your first term is. And if you wanted to, you could say a sub 2 equals 13 or a sub 3 equals 23. Typically, you want a sub 1 just because you want the first term. But again, it does not matter. But you have to define one of the terms. That's one of the big uh-ohs on students on the exam on this one is they just mess up. A sub n is equal to a sub n minus 1. We're always going to do that, okay? This is always telling me I'm taking the previous term. So if this is a sub n and this is a sub n minus 1, that's the previous term. So if this is 6, this is going to be the fifth term. If this is 8, this is going to be the seventh term. Okay, well, what are we doing to that previous term? Well, all you're doing is adding 10 to it. So if I want the 8th term, well, first I got to figure out what the 7th term is.